Hi, I'm Bradley Gordon. This is my video lab report for Lab 4, Circuits and Capacitors. So the goals of this lab report are to predict what will happen in circuits with resistors in parallel or in series, and we wanted to use the simulator to explore how ohmic resistors and capacitors act, and we use voltmeters and ammeters to measure current and potential differences, as well as comparing experimental to calculated data. So for our results, we got a 2-resistor circuit. Current was 0.02 amps. The calculating experiment values matched for the current and potential difference, and the more resistance in an RC circuit means more time for a capacitor to charge and discharge, and the magnitude of current is time dependent and based on our exponential equations, and our RC was 5.98 seconds. Our node rule is that the current going into a junction equals total current leaving that junction. Our loop rule is that the potential difference round trip for a circuit is 0. And for our electrical resistance, Ohm's law is used when constant resistance. And then there's also in parallel and in series equations. And our capacitance, which measures the amount of charge that can be stored in a capacitor per unit of potential difference. For models, the system was ammeter or voltmeter, which are measuring devices. Our surroundings are circuit, and our initial conditions were the volts of the batteries and how much the resistors were resisting. And for our assumptions, resistance of wires and ammeters is negligible. For our simple circuit, we had 2 batteries at 1.5 volts, 2 resistors at 4700 ohms, and 2 ammeters, and our predicted I, which was V over R, was 0.0204 amps, and our actual I was 0.02 amps. When we reversed an ammeter, it became a negative 0.02 amps due to the reverse of polarity. In our open circuits, we predicted a potential difference of 3 volts and a current of 0 amps because when we went across 2 batteries, that added up the 1.5 volt battery to be 3 volts, and the voltmeter had a lot of resistance, so it went down to 0 amps for the whole circuit. And this matched our experimental. For potential differences on a circuit, there's only a change of potential difference when we go across a battery or a resistor, and you can see going across 2 1.5 volts batteries gives us a 3 volt difference. Going across the 47 ohm resistor gives us negative 0.96 volts potential difference, and for the 100 ohms, it's negative 2.04 volt potential difference. And when it just goes across the length of the wire, it's 0, and this satisfies the loop rule as we added up the potential differences to get 0. For an ammeter in parallel, when it's in parallel with the 100 ohm resistor, some of the current can bypass the resistor by going down the other path, and the current would then increase from 0.02 amps to 0.06 amps because it's not all being resisted, and you can see some math to back this up. When we calculated resistances, we used experimental values in Ohm's law, which was R equals delta V over I, or volts over I. And in the 47 ohm resistor, we got a resistance of 48 ohms, 100 ohm resistor, 102 ohms. For an ammeter and wire, the resistance was 0 ohms, and we found that the values were higher than expected because the ammeter is not precise. In our RC circuit, we constructed it using those components, and our results was that in the 10 ohm resistor, our charge time was 15.2, and the discharge time was 15 seconds. And for the 20 ohm, our charge time was 25.5, and discharge time was 27.1 seconds. And the two were similar for both resistors, and we also found that the more resistance means more time for charges to move, which means more time for potential difference to decrease, leading to a longer time to reach 0 current. For finding the time constant of the RC circuit, we constructed an RC circuit using those components, and our objective was to charge a capacitor and measure potential difference across the capacitor. We removed the battery to pause the circuit, and for each second, we recorded potential difference across the capacitor as the capacitor discharges. So we plotted the potential difference at time t over the ln of the potential difference at time t over the initial potential difference versus time, and our equation gave us the slope of negative 1 over RC, and so our RC time constant can then be solved for, and by using the slope, negative 0.1671, and then we solve for RC to be 5.98 seconds. For our discussion and our possible sources of error, we found that there weren't that many due to the simulation, but some of them could have included lack of precision with the ammeter because we only rounded to the hundredths place, and we also could have rounded during our calculations when we mess up our numbers a little bit, and there also could have been errors with timing the charge and discharge times for the RC circuits. What if we were doing this lab in real life and using an actual ammeter instead of an ideal simulated ammeter? What's the difference about a real ammeter and how it would have affected the circuits you hooked it up to if you did this lab with the real ammeter? So if we had used a real ammeter, the wires would have some resistance, and we would have decreased the current in the circuit slightly, so the current readings would have decreased on the ammeter due to this added resistance. What if you were doing this lab in real life and used a real battery to charge a real capacitor with no resistor in the circuit? How quickly would our ideal model predict the capacitor to reach full charge? Would this prediction happen in real life? Explain. So the ideal model predicts the capacitor will reach full charge basically instantly. And this really wouldn't happen because wires and batteries have some resistance, which would increase the time for the capacitor to reach full charge, and the capacitor's resistance would also affect that time. So some conclusions are that ammeters have almost no resistance, accurate values for ideal circuits, the wires in the ammeters must be conductive enough to have almost no resistance, and for currents and voltage at different locations in a circuit with capacitors and resistors, they are time dependent. and they decrease exponentially with time. And the node and loop rules are tools used to accurately observe circuits. Thank you.